Welcome. In this walkthrough, we'll look at a real-world build solution for a high-frequency trading engine, powered by EC2 Image Builder. High-frequency trading lives and dies on latency, so every machine image has to be tuned for the exact hardware it runs on. Our challenge is to produce 6 distinct images, 2 operating systems, Ubuntu 24.04 and the anticipated 26.04, each compiled for 3 CPU families, AMD, Intel, and ARM Graviton. The elegant part is that we'll assemble all 6 fully automated pipelines from only 8 reusable building blocks. Let's see how Image Builder makes that possible. Before the architecture, let's answer a fair question. Why use EC2 Image Builder at all? You could build an AMI by hand in the EC2 console, or script it with the AWS CLI. Both work, for simple cases. But the console produces a snowflake image, hand-tweaked, hard to reproduce, and impossible to audit 6 months later. Scripts are better, yet they're only ever as good as the person maintaining them, and they balloon in complexity as combinations multiply. EC2 Image Builder is a fully managed AWS service that automates the creation, management, and deployment of customized, secure, and up-to-date server images. It gives you versioned recipes, so the inputs always define the output. It compiles natively on the architecture you choose. It runs your tests and an Amazon Inspector vulnerability scan as part of the build, and it will only distribute an image if every configured test passes. And it ships finished images across regions and accounts from a single configuration. For 6 images, on a schedule, behind a test gate, compiled natively per architecture, this is precisely the scenario Image Builder was designed for. The entire solution rests on 6 resource types that nest together. Understand how they relate, and you understand the whole design. First, a component. In the official documentation, a component defines the sequence of steps required to either customize an instance before image creation, a build component, or to test an instance afterward, a test component. It's a plain text YAML document, and it's the smallest reusable Lego brick in the system. Components run on the instance through AWS Task Orchestrator and Executor, or OSTO, the managed application that performs all on-instance work. Second, the base image, the operating system and starting AMI your build runs on top of. Here, those are AWS-managed Ubuntu images. Third, the recipe. A recipe is a document that combines a base image with an ordered list of components to produce the desired configuration. It's the blueprint. It defines what to build. Fourth, infrastructure configuration. The EC2 instance's Image Builder launches in your account to build and test, including instance type, IAM role, and network. It defines where to build. Fifth, the distribution configuration, which regions and accounts the finished image ships to. It defines where to ship it. And sixth, the pipeline, the automation framework that ties a recipe, infrastructure, and distribution together on a schedule. It defines when to build. Recipe, infra, distribution, pipeline, what, where to, and when. So here is the entire solution expressed as a handful of numbers. 8 components, are reusable building blocks, 4 base images, 6 recipes, 1 per operating system and architecture combination, 3 infrastructure configurations, 1 for each CPU family, a single shared distribution configuration, and 6 pipelines that orchestrate it all. Notice how few moving parts there really are. 8 components fan out into 6 production images. That economy is the whole point, and the next few slides show exactly how the pieces connect. Those 6 recipes come from a simple matrix, 2 operating systems multiplied by 3 CPU architectures. Across the top we have AMD x86-64, Intel x86-64, and ARM ARM64. Down the side, Ubuntu 24.04 and 26.04. Each cell is one recipe, named clearly, Recipe U24 AMD, Recipe U24 Intel, Recipe U24 ARM, and the same 3 again for 26.04. 6 cells, 6 recipes, no ambiguity. Why 2 operating systems? Ubuntu 24.04 ships the Linux 6.8 kernel. The anticipated 26.04 release is expected to bring 6.14 or later, with stronger IO_Uring and EBF support, both highly relevant to the kind of kernel bypass networking and low latency event handling that next-generation trading strategies depend on. Building both lets the team evaluate and migrate on their own timeline, without rebuilding the whole system. Let's trace the assembly path from raw materials to a running pipeline. We start with a base image, Ubuntu, in either x86-64 or ARM64. To that we add our components, the build steps and the test step, drawn from our 8 building blocks. A base image plus an ordered set of components equals a recipe, the blueprint that says what to build. But a blueprint alone doesn't build anything. We combine that recipe with an infrastructure configuration, which says where to build it, and a distribution configuration, which says where to ship the result. Bring those three together, recipe, infrastructure, distribution, and you get a pipeline, the orchestrator that runs the build on a schedule and produces the finished AMI. Every resource in this solution exists somewhere along that path, and once you can see the path, the rest of the design is just detail. Now to the heart of the reuse story, the 8 components, in 3 groups. The first group is shared build steps that run on every single recipe. There are 4. HFT Engine Core deploys the trading engine binary and its dependency libraries. Kernel tuning applies the low latency essentials, isol-ICLPS, nose_full, raku_knock-bias, and huge pages, to keep critical cores free of interruptions. Network stack handles ENA driver, DPDK, and XDP tuning for the fast path. And security hardening applies sys level 1 hardening and trims the attack surface to a minimum. The second group is CPU specific, and only one is selected per recipe. Optimize AMD compiles with March Zenver4 and tunes NUMA and SMT pinning. Optimize Intel targets Sapphire Rapids with AVX 512 and TSX hints. Optimize ARM targets ARM E9A with LSE Atomics and SVE and Neon SIMD. The third group is testing, a single component, HFT validation, which runs latency benchmarks, engine smoke tests, and an Amazon Inspector vulnerability scan. Do the arithmetic. Each recipe is 4 shared build steps, plus 1 CPU-specific step, plus 1 test, 6 component references, drawn from a pool of just 8. Here are the 3 CPU-specific components as they actually exist in the account. They're deliberately almost identical in shape. Each is an auto-execute bash step that writes compiler flags into the environment, into /etc/profile.d and /etc/environment. What differs between them is only the March target and the SIMD flags. The AMD variant sets March Zenver 4 and disables NUMA balancing so cores can be pinned explicitly. The Intel variant targets Sapphire Rapids and turns on the AVX 512 family, AVX 512F, AVX 512VL, AVX 512BW, AGX 512DQ, while still feature detecting at runtime. The ARM variant targets ARM9A with outline atomics, so LSE atomic instructions avoid the lock and retry storms of older load-linked, store conditional sequences, and lets the compiler emit SVE and Neon automatically. This is exactly why the design insists on distinguishing CPU at the infrastructure layer and compiling natively. The same source, 3 sets of flags, 3 native builds, and 3 images, each genuinely optimized for the silicon they'll run on. The 4 base images are all AWS-managed Ubuntu AMIs, used as the starting point for the build. We have 2404 in x86-64 and ARM64, and 2604 in x86-64 and ARM64. The x86-64 images are noble. The 2604 line is the anticipated plucky release. Here's a subtle but important point. AMD and Intel both run on x86-64, so they share the very same base image. We do not need a separate AMD base and an Intel base, because the CPU-specific optimization happens later, through components, at build time. That's a direct consequence of how Image Builder layers components on top of a base image, and it's why 4 base images are enough to feed 6 recipes. 3 infrastructure configurations, 1 per CPU family, and this is where the compile natively principle becomes concrete. The official documentation describes infrastructure configuration as the settings for the EC2 instances Image Builder launches in your account to customize images and run validation tests. So we make those instances match the target architecture. Infra AMD builds on AMD EP instances, C6A or C7A2's large, so the compiler Zenver 4 optimizations run on real AMD hardware. Infra Intel uses Intel Xeon, C6i or C7i, so the AVX 512 instruction set is genuinely available at compile time. And Infra ARM uses Graviton, C7G or C8G, for native ARM64 compilation with SVE and Neon. All 3 share the same EC2 Image Builder role IAM role and build inside a private VPC subnet. Specifying more than one instance type per config, as we do here, also lets the service draw from a larger capacity pool and reduces transient build failures. With the recipes and infrastructure defined, the pipelines fall out almost mechanically. Each of the 6 pipelines is one recipe, paired with its matching infrastructure configuration, plus the single shared distribution. So pipe U24 AMD is recipe U24 AMD, on Infra AMD, distributed by dist HFT. Pipe U24 Intel pairs recipe U24 Intel with Infra Intel. The ARM pipeline uses Infra ARM, and the same 3 pairings repeat for the 2604 line. Same clean pattern, 6 times over, and because the distribution is shared, there's exactly one place to change how and where every image ships. Let's look at the real wiring behind one pipeline. On the left is the recipe. It names its parent image, the AWS-managed Ubuntu 2404x8664 AMI, and then lists its components in order. And order matters. Image Builder installs components in the sequence you specify. Engine core, kernel tuning, network stack, security hardening, then the AMD optimization step, and finally the validation test. 4 shared, 1 CPU, 1 test. On the right is the pipeline. It's enabled, and it runs on a cron schedule, 5 a.m. every Monday. But look at the start condition. Expression _match _ dependency _updates _avable. This is a powerful feature. The pipeline fires on schedule, but only actually builds a new image when a dependency has genuinely changed, a component was updated, or the base image was patched. If nothing changed, there's no pointless rebuild. The infrastructure block at the bottom ties this pipeline to its AMD instance types and the build IAM role. All 6 pipelines share this same cron, so they build in parallel, each only when it has a reason to. Let's bring it together with the 6 principles that run through the whole design. 1. Base image sharing. AMD and Intel ride on the same x86-64 base image. Differentiation happens through components, not separate images. 2. Maximum component reuse. 5 of the 8 components, the 4 shared build steps plus the 1 test, are reused across all 6 recipes. You write them once. 3. Infrastructure distinguishes CPU. Architecture-specific code is compiled on matching native hardware, because native builds are more reliable than cross-compilation. Or, a unified distribution. All 6 pipelines share one distribution configuration, so shipping is managed in a single place. 5. Clean version management. Upgrading from 2404 to 2604 only requires new recipes that swap the base image, the components and the infrastructure configs need no changes at all. And 6. A unified schedule. One cron expression triggers all 6 pipelines to build in parallel, each rebuilding only when its dependencies change. That's the solution. 8 reusable components, layered onto 4 base images, composed into 6 recipes, compiled natively across 3 infrastructure configurations, and shipped through 6 scheduled pipelines, turning a fully managed AWS service into a low-latency image factory for high-frequency trading. Thank you for watching.